So, well, I don't want to make an introduction. So, Gérard Berry will give us 3 hours of lectures on circuits.
Several things.
Very nice things. So.
No, j'ai un micro, moi. So thank you, Pierre-Yves, and hello, everybody. I'm really happy to be here because I've not been doing formal verification by theorem proving or proof checking in the last years, but this is the way I started. I started my career basically after some assembly programming that went nowhere in Stanford, where they had a broken leg, not broken, but twisted knee. And I called the guy, I just had this number, and he told me, I cannot help you because my house is already full with friends. But if you want, I have a spare terminal in my office, and I can give you some work. A terminal in '72 was something completely original. And I went to the office of this guy, and he made me work on the very first version of LCF, Stanford LCF. And I did a proof of bubble sort, and this guy was Robin Milner, who I used as a personal teacher for 2 weeks, and that was pretty good. And then I did quite a lot of lambda calculus with Pierre-Louis Curie in particular, working on stable function, I was doing things similar to Girard, by the way, at the time. Coherent spaces and stable function are the same thing, and then working on categories and other models. And then I switched to real-time programming because I thought that there was more future. It was very interesting for me to program cars and robots and airplanes and so on. And I didn't know I would be catched up again by formal verification in the lambda calculus. So in 1989, I went to work with Jean Vuillemin digital equipment, and then I discovered the real exciting world of circuits. And I devoted a part of my life to circuits, first at Digital, and then at Synopsys, Cadence, Intel, and then at Esterel Technology, a company we created for circuit design and circuit formal verification. And again, I was caught up by proof theory and analysis of cyclic circuit. I will show you today and tomorrow is what I call electrical Curie-Howard. And the main result will be that the electricity is deeply intuitionistic. And so I will show you that this is totally justified, and Curie-Howard is justified, and that the circuit is really a proof engine in intuitionistic logic theory, but without quantifier and without higher order. But I think it's very interesting. And I also think that the thing I will show you give very interesting exercises for Koch, for formalization, because I don't think they are trivial. I think they are really interesting and beautiful mathematically, and I will try to convince you of that. So if you don't know circuits, you won't have to know much more, because I will explain you what you need for circuits. Circuits is a big world, complex, but it has simple parts, and that's what I want to do. So the first talk will be about circuit and two-adic numbers. This is something done by Jean Vuillemin, in fact, in which I participated a bit. And we developed together a language called 2Z, which is very, very nice and used by absolutely nobody. And if somebody wants to improve what you have done, you will see the theory. The theory is absolutely fun and nice. And I think it deserves a better treatment, in particular in Koch. So Jean is here, so I use this slide in my courses at Collège de France, which are supposed to explain all of that to an arbitrary public. Collège de France is an arbitrary public, mostly by internet, by the way, with a huge number of downloads from professors, teachers, curious people, and so on. And one of my goals for the future would be maybe to try and teach Koch to the normal people, which is not something easy to do, I guess. Koch and formal verification and so on to normal people who will not become users, but who want to understand what it is about. And that's fundamental if you want to have application in industry anyway. So the paper is called Circuit and Numbers, and I borrowed much from it, but I try to make it easy. So what is a circuit? There are two kinds of circuits, combinational circuits, digital circuits. clock digital circuit. There are other kind of circuits, but they don't really exist. This one, everything you have in your pocket is in this category. So basically, a circuit is a set of gates and wires. And gates are, say, OR. Remember the shapes. OR is like that, AND is like that, XOR is like that. And there will be MUX, which is a rectangular, which is if then else. And so you have wires, X, Y, Z, and so on. And this wire fan out to several gates. And there is a fan in from several gates to a gate, and so on. So they are just, you can use them as a Boolean diagrams. But they are diagrams, and they are equations at the same time. So as diagrams, and I will use this abbreviation for the circuit or any of its cousin, equivalent cousin. So this circuit is acyclic. That is, the graph has no cycles. And that's the standard way of doing things. But in the second and third course, we'll see that cyclic circuits are immensely interesting. And this is where intuitionistic logic plays a major role. So, but in the tradition, acyclic circuits are the rule because they are easier to deal with. But I will show you that we lose out of that. So there are two ways to draw circuits. One is to make a graph, and the other one to put a Boolean equation. And these two ways give two very different semantics. So the electrical semantics, basically, in a gross simplification, you put values, which are voltages, 0 volt or 1 volt, and according to the laws of electricity, electric value changes propagate at speed of light in the conductor, more or less. And, but the most important thing is that they go parallel. The only thing which is not trivial is sequence. The only thing which is trivial is parallel. So circuits are exactly the opposite of software. We'll see that at several occasions. So the only thing you can deal with is parallelism, really, easily. And so here you see all these wires get fed in parallel. And then the gates compute, and the gates may take some delays, the wire also. And for example, here you get this output to 0, S to 0. Then maybe you get this output to 0, because that's an AND gate, and you get this output to 1. And since you have a 1 here, you may have a 1 at the output here. And maybe before the third input comes, and the third input is actually a 0, but it's useless. Okay? So it's propagation in parallel with delays, and delays that are bounded. It's not asynchronous as in internet. The delays are known and bounded and understandable, and CAD tools play with that and tell you exactly what is the worst case delay. And the worst case delay is typically due to one path only. So which means that you design a circuit, when you design a circuit, there is one expressive part, and all of them are free. So that's very different from software. You are maxing things, you are not adding things. So everything which is not critical is free. That's another view of circuits, which is very useful. Good. So the critical path is the path of maximum stabilization time, which of course depends on the particular delays. In one technology and another technology, it may be different, but it always exists. Good. So now we have two views. The one with the critical path, there are delays, and the one without delays, we solve the equation. We assume some magical God solves the equation. And the thing that makes computer science work is that these two things coincide. That is, if you wait long enough, if you went for the critical delay, the circuit does compute the equations. So the circuit is basically a proof engine to compute the equations. And that's the way you should see it. And of course, because there are several inputs, the circuit gathers several proofs in a single network. Okay? So it's in fact a proof network. And you can see a circuit as a folding of all possible proof trees. Essentially, when you say that this output of the gate is false, you apply the rule, the logical rule, that if you have why do I say? Wait, that's XOR. If you have two inputs in XOR that are true, the output is false. Good. And so this point of view is not classical. Circuits, viewing circuit as proof engines is not classical. They usually the hardware field has a strange mathematical concept and a quite strange vocabulary, but you can make sense out of it. Good. So circuit is a parallel vibration machine. Vibration means propagation of waves, of sound, of light, of whatever, in predictable time. It's completely different from a synchronous parallel. And it's much more easy to deal with, actually. And there is another parallelism, which is synchronous parallel. You just magically solve the equation in 0 delay. And circuits have the two, and they agree. Good. Now, if you want to do more than 1 bit, you can go, for example, in space. And if you do that, you see the critical space of the critical path of carry propagation becoming very long. And that means that this is not usable in practice, and that's not the way the computers are done. And there are lots of ways to do additions, and it's a fabulous thing. And you can spend hours on addition. But I show you only one, the von Neumann adder, which does dichotomy and really use of parallelism. So you take the lower the bits here, and the higher the bits here, and you add them in parallel. But you do two additions in parallel for each of them. You do a plus b and a plus b plus 1 at the same time in parallel. Why? Because the two results get at the same time here, and then in function of the carry, you can decide whether the incoming carry of this guy, the higher order bits, is 1 or 0. That is, you speculate. You pay too much energy to pre-compute a plus b plus 1 here, a plus b and a plus b plus 1, and in function of the result here, you select, and this is the mux selection box, you select the right thing. So the whole game of circuits is mostly to compute too much, which these days too much, and to throw away the bad part just to save time. This is not anymore the case because the main problem with circuit is energy, and when you compute too much, you spend too much heat. So there are a lot of balance. So okay, so if you do this dichotomy, you get the von Neumann hardware, and here it is for 4 bits, and you go logarithmic instead of linear, which is optimal, but then you realize that you can also do addition in constant time, whatever the number of bits here if you don't care for the result instantly, and you can discover and let you discover that yourself, that multiplication is as fast as addition, and that's absolutely not trivial. You can spend quite a lot of time before realizing it. Okay, but anyway, you know enough about combinational circuits. Now time. So there is a time inside the combinational circuit, and we see that the cyclic circuit analysis is about this time. There is another time. The other time is the clock cycle. So assume your circuit is able to do any addition in 1 nanosecond, then you can make one addition every nanosecond, which means you can use a clock at 1 gigahertz to do your additions. And here is another way to do addition. Instead of doing it in space, you do it in time. And this notation say, I will pass the numbers lower the bits first instead of higher the bits first, as usual. Because when you go higher the bits first, the carry goes the wrong way. Okay? You can also do higher the bits first, but it's very complicated. When you do lower the bits first, it's very simple. You say 1 plus 1 equals 0, carry, 0 plus 0 plus 1 equals 1, and so on. And so here you use a thing which is called a register, or a memory point, which is simply a sampler. That is, you compute A plus B, you get S, and you get the carry. And here, when the clock edge comes in here, the clock is a rectangular shape this way. When the clock edge comes in, this circuit swallows the input and puts it in the output for the next cycle. It's a 1 cycle delay, basically. It's a delay in time, which is exactly what you want for a carry. So this guy here is computing the sum, the carry and the sum of these two numbers. And remember that this two number may be infinite, which was not true before. And so you can go in time, you can go in space, or you can go in any mixture of time and space. That's a major game in circuits. And we shall see that this game can be made very beautiful mathematically. So the notion of time we have is multiple. So you have a logical time, which is you don't care about the internal timing of the circuit. You care only about clock cycles. And you say that whenever you put an input, you get an output. Whether you get it right away or the next cycle doesn't really matter here. You get it right away. And in the electronics, this is the view of a programmer, basically, and the view of a guy in electronics is this one. It takes some time. But if you put your clock at the right frequency, there is no overlap, and the results are exactly the same. Okay, once you know that, you will understand everything about circuit. And this is hard to do, by the way, but that's different. Good. The clock is not necessarily regular. Huh? The idea that a clock is regular has been broken long ago, and for example, your telephone, the main activity of your telephone is to slow down everything whenever possible, just to not empty the battery. Okay, now we have these numbers written low order bit first and infinite. They have a name, so they are called two-adic numbers because we are in base 2. And where do they come from? They come from Hensel. I don't remember exactly the date, but you should know, Jean. And the question that was asked was the reals is a compilation of the rationals, and is it the only one? And the answer is no. You can have these numbers written low order bit first for any prime basis. That is 2-adic, 3-adic, and so on. And Ostrovsky's theorem, showed much later, showed that these are the only completion of the rationals. Now, seen from a computer scientist, the names are very badly chosen, at least the real, because the real is the only number that don't exist. Okay, there is just no way to build reals in computing, while all the p-adics exist. And they are very easy to build, and I just showed you the addition of p-adic numbers. They are simply infinite stream of 0 and 1. So they are extremely basic objects in computer science, while they are, and they are very interesting. Alain Cohn, in a discussion with Jean-Pierre Changeux in Matière à penser, quite interesting books between two different views of the science. Alain Cohn, who knows about two-adic numbers, I think, better than myself, said that they are beautiful. They have the wonderful computation rules. They are extremely useful in mathematics, but they have no physical interpretation whatsoever. And we shall show that this is the contrary for us, which means that reals have no computer science implementation meaning whatsoever somehow, while two-adic are the natural implementations of numbers in computer science. But the problem is that this is not in nature. When Alain Cohn was talking about physics, it was Mother Nature, basically, the physics we see around us. Here it's a physics we build ourselves. It's not clear that you have two-adic adders in nature, not clear, but we build them. So it's synthetic physics. Good. So you can see two-adic numbers are infinite arithmetic, integer arithmetic with Boolean algebra. And that's how they differ from three-adic numbers or five-adic numbers, and that 5 and 3 don't have the Boolean algebra. And that's why two-adics are very important for us. So what are they? Well, the first thing, they are low-order bits first, okay, and the operation goes from left to right. The carries goes in the right direction. And plus and multiply are just as usual, you push them to infinity. In C, you would call them unsigned, and that would be exactly the same thing. So 0 is a set of zeros, and when there is a period, we write it with parentheses, 0. 1 is 1 followed by zeros. Minus 1 is only 1s. Why? Because if you do 1 plus minus 1s, you get zeros. That's all. So you don't have to think in two-adic numbers. Huh? You have to be as stupid as a kid. If you are not able to be as stupid as a kid, you will have trouble with this talk, okay? 2 is 0, 1, 0, 0, because if you add 2 in the beginning instead of the n, as usual, you multiply by 2, fine. So that means that minus 2 is 0, 1, 1, 1, 1, and if you add 2 to minus 2, you get 0. So that's no problem. Let's look at this guy, 1, 0, 1, 0, 1, 0, periodic. And so you have to be very stupid. Huh? That's the difficulty of the game. So you say it is 1, 0 plus 0, 0, 1, 0, 1, 0, 1, 0. But 1, 0, that's 1, and the other one is 0, 0, 1, 0, 1, 0. So it's exactly 4x, because adding 2 zeros in the beginning is multiplied by 4. So this guy satisfies the equation x equals 1 plus 4x, and you have no choice, it's minus 1/3. That's, you have no choice. Huh? So Of course, the other one is minus 2/3, because if you add the 2, there is no carry whatsoever. You get 1, 1, 1, 1, 1, which is minus 1. So this guy is minus 2/3. You can see also that it's multiplied by 2 in the beginning because you put a 0 here. That's the same. So this guy is minus 2/3. Okay, so you can check that you can build all the P over Q with Q odd. And you can play nice game. It's not instantaneous to compute the binary representation of P over Q. You look at Vuillemin's course, for example, and they will tell you, but Euclid did a lot on that. And of course, 1 over 2 does not exist. We have a ring only. 1 over 2 does not exist because its first bit should say x0 plus x0 equal 1, and that's not possible. So you can divide by any odd integer, but not by even integer. You can do that in a ring, in the field, but we don't use the field here. Big difference with real, there is no order compatible with operation. You cannot say that minus 1 is less than 0 than less than 1. That makes no sense in two-adic numbers. They are completely different beasts, okay? They are really different beasts from the reals. That you cannot do. What is interesting is that they are a Boolean algebra. So you can see a number like that as a characteristic function of a set. That's what you do in C when you say unsigned. So for example, minus 1/3 is the set of even numbers. And minus 2/3 is a set of odd numbers. Okay? And once you do that, you see your gates. What are your gates? They are AND gate, OR gate, NOT gate are just the intersection, union, and complement of sets. So you can play with sets and you can play with arithmetic at the same time. This is what is very interesting. This is the fundamental thing in two-adic arithmetic. X plus not x equals minus 1. Why? Because x has 0 and 1, and not x are exactly the opposite. When you add, you would never have any carry, and you get 1. And so x plus not x equals minus 1 is the fundamental arithmetical logical relation. And this you should never forget. Most calculations are done out of that. Good. Here is why. Okay, but that's not. My slides are made for non-mathematicians, and so don't worry. Sometimes if you find it a little bit easy. So in Esterel, Esterel is a real-time language to fly airplanes. So I thought I was done with complex semantics and fancy mathematics and whatever. Not true, because I had Gonthier in my team. And that was a very good idea for other reasons. But at some point, we had to compute an operator in the language. It's an imperative language with exceptions and so on. And the key encoding is that any statement will return an integer code, which is basically 0 if I terminate, 1 if I not yet terminated, and 2 if I raise an exception, and 3 if I raise an exception at level 2. De Broglie indexing of exception, basically. And the beauty of this encoding is that the semantics of parallelism is max. And that's much simpler than in asynchrony. So we have to compute max of P and Q. But when you do static analysis, you have to compute a big max, which is a set of maxes of the code that may be returned by each branch. When you do static analysis, you don't know the inputs, but you look at whatever will happen. You have to do that for all sorts of reasons. And you have to compute this set here. And in the Esterel compiler, I had written loops to do that. Of course, as a beginner, you have to be beginner, but not too much. I had written loops, and Georges Gonthier came to my office and said, oh, I can really speed up the compiler and simplify it by using unsigned number and this expression, max of xy equals x or y, and x or minus x, and y or minus y. So I fired Georges out of my office once more, and once more I was wrong, and I tried that, and the compiler was about 20% faster. I said, hey, Georges must be right, so what's happening? And then I discovered this was indeed two-adic arithmetic, because this is a two-adic formula. And the bit sets were encoded as unsigned in C, and this is the two-adic formula. Why is it true? Because max of xy is in fact the set of members of the union of xy which are bigger than the maximum of the two means. Why? Because if you are bigger than the other mean, then the max of yourself in your other mean is yourself, and so on. So that's very easy to see. And being bigger of the max of the mean is easy, because what is the mean of a set? X or minus x is the set of number bigger than the minimum of x. Why? Because you take x here, you take minus x. So what is minus x? Minus x is go to the first one, keep it, and invert all the other bits. So what is x or minus x? This is simply 1 over the mean. Okay, so when you take the intersection of x or minus x and y or minus y, you get all elements bigger than the max of the two means. And then if you intersect with x of y, we get exactly the right set. I said that's interesting, because I removed 2 loops to replace them by 7 machine instructions. That's quite nice. And this is playing with two-adic numbers. It's a fun game, really. And that turned out to be absolutely major, because when working with Jean-Villemin at DEC, we discovered that, in fact, Esterel was not a language for software, but a language for hardware, or more exactly, that software and hardware became exactly the same thing, and that we had to compile Esterel, and then I couldn't write loops in hardware. And I had to do this max operator to synchronize, and this is the magic max operator. And one of the subjects I have already given to Henri, who is here, is to make the proof in Coq that the Esterel compiler is right. And the key of the proof is certainly in this operator. This is computing a max in a super clever way, essentially because it propagates 0 in a very nice way. You will see in the constructive part why propagating in 0 is important. Good. So let's come back to two-adics. Two-adic is a metric space. The matrix is a very old metric. It says that if you have 2 infinite streams, you look at their common part. Well, if they are equal, their distance is 0. And otherwise, you look at the first difference, n, and you say that the distance is 2 to the minus n. The longer is your common prefix, the better you are. So here, for example, the distance between these two is 1 over 8. Good. So first lemma, then 2z is ultrametric. So that's completely different from R. It's ultrametric, which means that the distance of x and z is less than the max of the distance of x and y and z. And this has all sorts of good consequences, like uniform continuity, and continuity becomes the same, and so on. So why is that true? You take the distance between x and y here, then you take the distance between y and z, suppose it is bigger. Then what it says that y and z are equal up to that point, and x and y are different from the first line here. So x and z are also different from this line here, and in fact this is exactly an equality. Good. In fact, d of x and z is mean of the d of xy and d of yz. Good. So what topology does that give? It gives the Cantor topology. It's another view of the Cantor topology. The open sets is just the finite prefixes, okay, finite words, and you take the cone out of finite words. So this is very normal in Scott theory as well, for the same reason. It's a Scott domain as well. And so that's the open set of this prefix. Okay, so that's the topology. It's compact. It's fairly easy to see. Actually, it's not that easy to see because it's Zorn lemma, basically, that this space is compact. And being compact is completely different from the real, that's for sure. The full space is compact. Good. What is a continuous function? By simply a function that preserves finiteness. That is, the nth bit of the output depends on finitely many bits of the inputs. That's completely standard and straightforward, no problem. That's the drawing to explain that to people who are not used to this. So continuity is preservation of information finiteness. That's very important. Okay, now let's look at what the relation with circuits. First, when you have first all the gates we are discussing are two-adic operators. And the most interesting one is the memory. Because why? because if you give a stream x0, x1, x10, and so on, the output of the memory, which is always supposed to be initialized to 0 by default, is 0, x0, x1, x2. So what is the memory? Memory, which is driven by that clock, okay? Oh, sorry, no, I'm too early. This is reminding you what is the memory, simply doing that. But you can check right now that the memory is multiplying by 2. Okay. So what is a synchronous function? A synchronous function is computable by a synchronous circuit. Definition. A synchronous circuit is what you can compute with a circuit, with any kind of circuit. Pentium is a synchronous function. Okay. The theorem is that a function is synchronous if and only if the nth bit of the output depends only on the nth first bit of the input. So if is obvious because it's from a circuit, but only if is absolutely not obvious. And this is the theorem we shall show then. So that's the definition of being computable by a circuit, if you want, is simply to be loosely contracting for the distance. Good. And we'll see the if. Let me see a use of that. It's well known in control theory whatsoever that you cannot make loops between circuits in an easy way except if there are delays somewhere. So this is quite well known. So what is a Moore circuit, Moore circuit, is a circuit so that any wire from input to output has at least one delay. Okay? So that's what is that thing? Is that thing that the function is strictly contracting. That is, the distance of the output is less strictly than the distance of the inputs. Good. So theorem, same theorem, a function is strictly contracting if it is computable, if and only if it is computable by a Moore circuit. Good. Now on Moore circuits, it's a fork theorem that you can always do feedback because you have delays everywhere. You can feedback and you never get any problem. If you don't have delays, you may have problem, but that's the second course. So what is this thing? It's very trivial. You have that here. Okay? But by definition of the distance, which is dividing by 2 every time you have a common part, this is equivalent to this. And then, sorry, I took the wrong Lifshitz, Lifshitz tells us that any Banach theorem, any Lifshitz function on a compact set has a unique fixed point. And this is the real explication why you can loop over delays. Okay? That's quite interesting because people never make the proof of that. And I asked several people in hardware, can you prove that to me? And they start waving hands and nothing happened. Good. Now, let's look at addition. Addition is this thing, is this Boolean equation system. That's not very, very tempting. Okay? Why this one and not another one? What does it have to do with addition? There is nothing like addition in there. Okay. So that, sorry, I have to, okay. Now, what you can say is that if you replace bits by two-adic as input, by numbered, by infinite streams, and you can view the addition over time, it is solving this two-adic equation, x plus y plus z equals s plus 2c. And that's fairly obvious. You can check it for the other. I mean, it needs to be shown. But basically, if you forget about bits and go to two-adic numbers, then you are talking about addition. And any addition circuit will do this, not just this one. And so you have an invariant which is really telling you what this piece of hardware does. And that's very important. So remember this one. Good. So what are the basic operators for circuits? This one, addition, FullAdder. This one, which is simply doubling. So memory is doubling. This one, which we call the Mickey Mouse register because of the ears on the side, which is putting two negations, one each side. So basically the first bit getting out is 1, and after that 2 negation cancel. So this one is outputting 1x, and this one is 1 plus 2x. And that's all. And that's all. That's all what you need, okay? Plus the set gate and or not. But now we are interpreting what is usually viewed on bit streams, on numbers. So let's show what kind of proof it gives. So this is the full adder, the adder over time we have seen. You put two two-adic numbers here and you get the sum. So the infinite sum, you get it on the output there. So if you have asked a hardware person to show you that it does add, well, start waving hand, explaining how the bits go and so on. That's not too hard. But there is a better way. Call this guy 2R, because this is the double of R. Okay, what the invariant of this circuit here, it's A plus B plus 2R equals S plus 2R. And here we are said by Mr. Alcovarismi, who told us, here is Mr. Alcovarismi, that's his grave, who told us that when you have equation like that, you can, he was the first one to, in his book Algebra, to say that, okay, you can simplify, so A plus B equals S. So that's a relatively easy proof that the thing had. Now let's go to a more interesting guy, which is this one. So this one you also find in books, but then understanding what's going on with the bits becomes a little more complicated. And in fact, this guy is doing subtraction. Why is that? Look, this is because of the two ears. This is 1 plus 2R here. Okay? So what is the invariant here? It's A plus not B plus 1 plus 2R equals S plus 2R. So you can remove the 2R. You say, but you remember now that B plus not B is minus 1. That's the fundamental equality between logic and addition. So you can rewrite that not B plus 1 equals minus B, and you can rewrite that into A minus B equals S. End of proof. You have absolutely no idea of what's happening to the poor bits in these circuits, okay? That's only a beginning. For the next cases, you will have absolutely no idea, even if you try. Okay, so that's interesting. That's a nice way to do proofs. I mean, proofs of elementary school on infinite numbers, fine, and algebra is good for us. So you get your subtraction. Now you can play the nice games. For example, you can say, oh, I can be a little more clever. I can play bits 2 by 2. I can add 2 bits here and in combinational part, and then carry this carry will go in space, and this carry will go in time. Okay? I go 2 bit by 2 bit. This is what you do in actual circuits. When you go 64 bit for 64 bit. Okay? So how you deal with that? You define the shuffle operator. You say that x shuffle y is x0, y0 is alternating the 2 bits. Okay? And then you have to prove this thing that S equals A plus B. What is extremely important, and that the whole idea of the language, is that the source code is the same. All others, I will show, have the same source code, S equals A plus B. And what we would like to have, and if somebody among you wants to do it, is a compiler where you say, okay, S equals A plus B, with this time-space compromise, your job. And of course, for example, what you can do, if you get 32 bits here, then you can replace this adder by the von Neumann adder to have a logarithmic thing. But that's optimization, no problem. But there is only one source, S equals X2B, whichever implementation you have. Here is a nice one, due to Jean, which I really love. You can do that with any circuit. Any circuit works this way. You just double all the registers. And what does this thing do? It does stereo, which means it interleaves 2 additions over time. Even bits addition 1, odd bits addition 2. That is, if you the shuffle, the result is the shuffle of the sum of the exactly wrong AE plus BE, and of course A. Okay, I got exactly the wrong way. Let me correct it. Plus BE and so on. Well, I will correct it on the slide that you put in 9. I don't know how I made this one, but I think you get the idea. So basically, by doubling each register, you do the addition of A, the addition of B completely separately, and you shuffle them in time. Stereo, because this is what you do in a stereo channel. The advantage you have appears in later optimization, because in optimization you start moving register around because they commute with gates and so on. It's called retiming, and that can be very useful for that. Okay, now assume now that we know, we have understood this addition is this one, this circuit is this one, it's addition over time, S equals A plus B, S equals A minus B, and we can play more game with them. So how do you multiply by a constant? So here is, for example, multiplying by 3. Why is it multiplying by 3? Because, very, very difficult proof, x plus 2x equals 3x. And that's not too complicated, I guess. But even Pierre-Louis seems to understand. That's more clever. Dividing by 3. So dividing by 3, you subtract twice the output. Why? Because the proof is very hard. Y equals x minus 2y, which is easily solved by any school child into y equals x over 3. Okay, it starts being a little less, little more interesting, and it's very interesting to try and look at the bits to see what they do. And that's another game. Preferably write an interpreter and look at, not by a pencil and paper. Huh? Of course, you cannot divide by 2 this way. That's more difficult. That's more difficult. Quasi-inverse, y equals 1 over 1 minus 2x. You need this minus 2 because you cannot divide by 2, okay? How do you do that? Well, you just rewrite the equation, y minus 2xy equals 1, alcovarismi, and y equals 1 plus 2xy, and you're done. You just have the circuit now. This is 1 plus 2xy. Okay? So that's a nice fixed point calculation that shows you that you have done this division correctly. Of course, you have a little problem, which is what is multiplication? Multiplication by a circuit, is it doable? The answer is yes. If you try to do the circuit yourself, it will take you some time, I must say, but the theorem will tell you how to do that automatically anyway. But you can try to do the multiplication, is fine. So that's cool. The proof is not difficult, I think. Good. The only problem with multiplication is that it's infinite. It has an infinite memory. Because, you know, when you multiply 4 digits by 4 digits, you get 8 digits, so you have to store them somewhere. But that's not a difficulty to have an infinite memory, because you have continuity. If you have interested only in n bits at the output, you can cut the memory, you know exactly where. You can cut your memory to the finite part, which is enough to get the output. And in general, you don't quite want infinite output in circuits, but you want modular circuit where you can decide after the design. You say, okay, here is my quasi-inverse. Please make it okay for 256 bits. Good. So it's contracting. Multiplication is contracting, so it's fine. It's definable. This is the best one, due to Jean again. This one is a pure marvel. Square root. So square root doesn't seem to be... square root in 2adic is something a little more complicated. But square root of 1 plus 8x. Square root doesn't seem to be that simple. But we have algebra, so we can say this is the right circuit, okay? What do you have? You have a square here. It's Newton, in fact, in some sense. You have a square here, you have a delay, you have a subtraction, a delay, and a Mickey Mouse delay here. Why is that true? If you look at the circuit, you say y is 1, this is 1 plus 2, and this is 2z. So y is 1 plus 4z. That's life. So you can square. So you can say y square is 1 plus 8z plus 16z square. That's all trivial, huh? Good. So now what is z? Z is here. What is z here? D is x minus 2z square. Okay, so replace y square equals 1 plus 8x minus z square plus 16z square. remove z square, you are left with y square equals 1 plus 8x, and that's done. And there, if you try to understand what happens to the bits, you're in bad shape. But you can compute square root of 9 and you will find 3, yeah, actually. It works. Not only it's proved, but it works. Okay. So the game, yeah, I think is not ended. There is a lot of room for imagination. We went to other tracks, but there is a lot of room to imagination. Is very nice. And understanding the bit level behavior is still a big problem. Okay, but how do we prove the theorem that a circuit is doable if and only if the function is contracting? Okay, then we have to do a little bit of a reminder of automata theory. Notation, f dot 0 is the first bit output by f for any input 0 something. Because f is contracting, the first output bit depends only on the first input bit. It may even not depend on it, but at most on the first input bit. So call that f dot 0, and f dot 1, the other one. And so if you want to run a word, f dot w, you run the word and you take the last bit of the word, f dot w. That's the notation. Now the dual is the predictor. You cannot predict what will you be when you are at some point in the calculation. You cannot, of course, predict what will your next output. That's the thing you cannot do in a contractive function. You cannot predict, but you can predict right now what will be your next output if the next input is 0. You can relatively predict. If I get a 0, then I will have this. If I get a 1, then I will have this. Okay? This is true for any automaton. So F0 is the 0 predictor. It tells you, given a word W, something you have already computed, it tells you the bit that will get out, it tells you now the bit that will get out of F if you input a 0 after W. It's a half predictor shifted backwards in time, but of course it cannot predict completely. It predicts relatively to 0. And same for 1. For U, it's the same. You say the U predictor is what will happen now that I have read W if I give U to the function. And I want to do that now, Good. So how to compute the predictors? It's quite easy. You build, quite easy. This is not the best way, but it's, of course, a way. You build an automaton. For example, you build a circuit of x goes 3x, this one. So you have 2 registers here. So it's a finite state machine. You can explore symbolically or explicitly. And if you explore it stupidly, you get this automaton. So that is exactly the multiplication by 3. So what is a predictor? It has exactly the same frame. But what you do is you shift the thing. For example, here, I want to know when I have the empty word, what will be the output on a 0. So here I compute the 0 predictor. So hop, I get it here. I take it from here, okay? I put it here. Now from this state, if I'm here, what will be the output? This one, okay? So I take it here and I put it here. Arrow per arrow, I do that. So essentially, I take values from the old automaton and I push them in the same skeleton. So that's the way to compute the predictor. Essentially, you are somewhere and you take an arrow. You say, I take the result of this arrow as my prediction. Good. So that's another automaton, and that's it. So that's another automaton. So then it is obvious that there is only a finite number of predictors possible. That will be very useful in the sequel. For a finite circuit, there is a finite number of predictors. Good. So what is the decomposition step? So it's basically building a truth table over space and time. That's the idea. So what you say is that for any function f, I can build the following circuit. Here I prepare in a register, which means I put years or not on the registers. I prepare the bit f.1, f.0. That is, if my input is 1, hop, this bit is ready to be output. If my input is tabulated. And what I have to feed in the register is the predictors. So this is a test whether the first bit is 1 or 0. And then I have to put the predictor here that will give me the next bit. Okay? And if you do that and you expand up to infinity, then you get an infinite circuit that computes exactly your function. So it's infinite. So multiplication, for example, you do that and you will get, it will be a little hard to compute the predictors technically, but it's doable. That's okay. This circuit has very good qualities. It's ultra fast. You see, the critical path is exactly 1 mux between 2 registers, ignoring the routing question, which will not probably be trivial, but it's extremely fast. The critical path is always 1 must. And what it does is basically, if you say the first x is 0, then this truth table, which is stored in this big tree, will be shifted by 1, stunk, losing half of its bits. So it's expensive in energy, of course. It loses, it's a truth table of all possibilities, and each time you get an input bit, you throw away half of the other bit. And the good idea is that you shift, you don't move your fingers, the circuit remains still, but the truth table shifts everywhere. So, good. Now, if you have finite memory, you know that you have finitely many predictors. And these inputs to register are predictors, so you can do sharing. You can do sharing like that, and then you have a finite circuit. So you have a normal form, basically, for every circuit using the predictors. That's good news. The bad news is that it's not very efficient. And typically, it may be double exponentially bigger than the circuit you start with. So it's probably improvable. Right? And the counterexamples are not hard to find. There are also good examples, and certainly this can be improved. But it proves the theorem.
What is a function with finite memory?
A function with finite memory is a function you can compute with a circuit with finite memory, and you will see that then the algebraic characterization, which is more fun. Here it comes. Now we can put the truth table of the function as a number. This number is like that. The trace of f is a number. What happens if what is the first bit of f dot 0 if I apply f dot 0? It's a truth table in time and space, but then linearized. Okay, you just go through the thing and you linearize. So that's f output on 0, 0, on 0, 1, on 1, 0, on 1, 1, etc. So you can define the trace of f of 0 plus 2f of 1 plus 4 times the shuffle of the trace of the predictor 0 and the predictor 1. Good. If you do that, lambda calculus will come later. You can also see this is a very interesting way to do things. So you can tabulate each function as an infinite word. But you can view it in several ways. You can view it as a two-adic number, or you can view it as a power series over z over 2z, over the two field elements, the field of 2 elements. Or you can see it as a power series over the field of 3 elements, if you want. Very different. Good. So the theorem is the following. F has finite memory if this power series is algebraic over z over 2z, which is the field of 2 elements. Okay? That's not trivial thing. That's not trivial because the next theorem is very interesting. The next theorem is before going to the next theorem, assume it is algebraic over z over 2z. What about z over 3z, where you say it's a power series with 0 and 1 and no 2's? Then it's never algebraic or rational. It may be rational or it may be not algebraic. And there is a nice theorem. I don't know whether this one can be put in Coq easily, by the way. That says the following. Instead of saying that this number is either a two-adic or a power series, why don't you say it's a real number, put 0, comma in the beginning. And you write this sequence of bits. You have a finite memory function, and you write all this truth table. What does it give to you? A transcendental number. And this is the best way known to generate transcendental numbers. basically, another way of saying that is that any finite automaton on 0, 1 generates a transcendental number. And that's quite interesting. And there is a full book on that, automatic sequences. And one of them, can you give me a piece of paper? Paul-Henri, j'ai besoin d'un papier. Non, un papier découpé. Ah ouais. Ah, this is good. So here is the new transcendental number. I don't know if you know this one. It's very nice. It's a very easy to build explicit transcendental number. You take this paper, you fold it, chunk, okay. You fold it again. It's always in the same direction. Always like that. Okay, it's monotonic. If you fold it once, the beginning will be the same. And no. Then you unfold it, and then you have curves, and you read them. Okay? If I turn right, I say 0. If I turn left, I say 1. So 0, 0, 0, 1, 1, 0, 1, 1, and so on. That's a transcendental number by this theorem. Quite nice. So Pentium, any automaton gives you a transcendental number, basically, by encoding in 201. So Pentium is a transcendental number, ARM is a transcendental number. Yes?
You attribute the theorem to van der Poorten?
Yeah. Alouche attributes the theorem to van der Poorten.
I thought it only came much later.
No, I think that van der Poorten
had the partial proof, and it's only the Adams.
Well, we can discuss that later, but yeah, I mean, as many theorems, the theorem was true, and the proof took some time to be true. But we have discussed that yesterday already. But that's very interesting.
So then attributed to Mendes France.
I'm not sure. I mean, is this crowd Mendes France, Alouche? No, Alouche, no. I mean,
he was the first one to conjecture that.
Mendes France was the first one to conjecture that. Absolutely. But I told them, can I see the proof? We say, you bet. You're not good enough in math, which is probably true. But that may be an interesting study to really prove things, because these things are immensely finite constructives and so on, okay? Now, I talked about synchronous functions, but there are also non-synchronous functions, like continuous functions. There are many things that are continuous, not synchronous. Can you deal with them? And the answer is yes. You can use what is called elastic time. I have a full course on that in my course at Collège de France. But I won't give only no detail here. But basically what you can do is to slow down time. You can play with time. And you can say that here, instead of representing a two-adic number by one series of 0, 1, you represent it by two series of 0, 1. The first one here, that's the value, and this one is called the valid or the clock, if you want. And you read the value of the number here only when the valid bit is 1. So your number is this. So this is well known in synchronous languages. It's called a clock in Lustre, in clock signal, a suspend in Esterel, and so on. We have been doing, it exists in elastic circuits as well. And you can do that. That is, your number gets slower, simply. And since your number gets slower, then you can do things like dividing by 2, just forget the first bit. It's not exactly dividing by 2, by the way. But you can forget the first bit, which you cannot do in otherwise. You can, and so on. You can do a lot of things. And a good question, which I never had the time to look at, is, but then I can do application of a function to an argument. A function is a big tabulation. And when I know the argument, I know how to count long enough just to get the bit. I just waiting for the bit in the function table to come to me, and then stunk, I can compute it. So I can compute application. So if I can compute application, can I do currying? Can I do lambda calculus? Then there is a theorem I never really understood by Baron Reich saying that there is no compact model of the lambda calculus. But of course, here you need to deal with finite or infinite sequences because you may never end the bits. So what is the relation between two-adic numbers and lambda calculus? This is still open. Okay. And of course, the theorem is that any synchronous function can be computed this way. So conclusion, thanks to Jean. Two-adic numbers are the right model for arithmetic circuit. They are the real things. The real numbers are called real numbers, but I would like to call the two-adic number the real things. Continuity, the metric continuity and synchrony are really fundamental. There is a lot of work to do. The structure of the predictor space. I say that a function is finite memory if and only if it is algebraic, so it's solution of some polynomial, the degree of the polynomial, the relation with the complexity of the function to do. Jean has work on that. Lambda calculus. So there is a lot of work to do. One of them being to put all of that in a nice implementation, in a nice proof system where these proofs are real proofs and so on. So I think that could be a good passe-temps for anybody. Thank you. Merci à Jean.
Questions?
I mean, the question how to get it.
Micro, ouais.
The question how to get it into lambda calculus. I mean, as long as you do not insist on least fixed points, you could take the continuous functionals as studied by Kleene. I mean, there is a theory, generalizing domain theory containing usual domain theory and also all complete metric separable spaces, and this is Cartesian closed. So you have a model of simplified lambda calculus, but not of general recursion.
That's true. But I would try to understand what is going on for general recursion. Where is the real problem? Because it seems to me that currying can also be done by counting. So, you know, I already had surprises when working with Pierre-Louis on models the calculus that were not functional. That were Cartesian closed category but not functional and so on, so I don't know.
But you have primitive recursion in the sense of Gödel's T, and even more, you have things like bar recursion in there, but you don't have general recursion which leads to non-termination.
Yeah. You may, if you have continuous, you can have non-termination. That is, you can have finite sequences that never get the next bit. That's possible, because the clock will have infinitely many zeros. So you may have non-termination here. In the case you did with synchronous function, no. But when you have a continuous, you see you have this valid bit. You have this valid bit. And if this valid bit is 0 forever, then you have non-termination. So you have partial sequences. So you can still have fixed points this way.
So 0 is not 0. 0 is around bottom. Strings or strings which may be broken.
Yeah. That is the continuous model is not at all a trivial extension of the original model. It's much more elaborate, and you need it if you want to go to lambda abstraction. Yeah, absolutely. But then you can have non-termination, and lambda XX will output nothing typically. But I'm puzzled by the compactness theorem of Baron-Recht and whether it has to do with this or not. Never had time to.
In the theorem that you attributed to Porte, there was a disjunction in the conclusion. It's either rational or transcendental.
Yeah.
Is that constructive or not?
The problem is that sometimes, is that constructive or no? I think it's not trivial at all. I don't remember. Is that constructive or not? Can you predict rationality? I'm not sure at all. I thought of that question long ago, but I didn't find the answer. But I think Alouche knows. I'm sure Alouche knows. And no, it might be undecidable. I don't know. Yeah, it might be undecidable. I would suspect that. Yeah. Bad luck, could it?
Other questions? Okay, so
let's talk about cyclic circuit analysis. And so that's a subject which has not been very popular before. because acyclic circuits were good enough for what people wanted to do. But a lot of people were trying to generate electronic circuits from higher level descriptions. In the beginning, circuits were made out of drawings, but now circuits have, you know, a modern circuit has between 2 and 10 billion gates, so it's hard to draw. And so they are all generated from programming languages. And even now you can generate circuits from thread C. If you write loops in C, you can have good compilers that get to good circuits now, provided it's not too much control, but data management is good. And so we were led to cyclic circuits by the idea of basically high-level programming languages. So let me recall you what is a combinational circuit. Combinational is a name like that. Basically, in the common sense, is a sort of acyclic network of gates with no memory here, and outputs in red and inputs in blue. Okay? And this circuit is acyclic, which means there is no loop in the graph, which makes it easy to compute the critical path. And easy is important enough because when you did with billions of transistors, you have the constraint that your computer-aided design system must answer you. And these systems are awfully complicated. Good. Now, a sequential circuit is the same with registers. That is, some inputs and outputs are plugged to memories, and they are not visible from outside anymore. So combinational, no memory, that's what we shall study first. And sequential with memory, and we'll see that this will not be that difficult to study. So there is a long program of short sections. The first one is Y cyclic circuits, and the second one is 3 kinds of cycles. So that's where I will start, and then we shall look at the logic of time in circuits, and the simulation as deduction, which is my version of Curry-Howard. And let's get rid of time, which will be the very important section, and then more stuff. So the first cyclic circuit of interest was this one. It came from people named Brock and I don't remember who, doing translation from high-level language, and they were doing some sharing. So assume you want to compute this expression. If C, then f of g of I, else g of f of I, where f and g are arbitrarily complex functions. If you do acyclic circuits, you need basically to code that. That is to have 2 copies of f and 2 copies of g. And of course, if you have FGH and all permutations, you need to have as many copies as written in the source code. Now you can say, I want to share the 2 Fs and to share the 2G. I can do it this way. Here I put a multiplexer, which are ifs and else. Okay, so if this guy is 1, then I take this input and I don't take the other input, and so on. And so this circuit here, that's the job. But it's perfectly cyclic. It has a topological cycle in it, but it works very well. Why? Because the condition will break this cycle. And the point is that the condition will break this cycle at different points according to its value. So if the condition is 1, all switches are up, and the trajectory is G first, then F, then output. Okay? If the condition is 0, it's the reverse trajectory here. So the cycle is never cyclic. It's always broken. It's always broken somewhere, but because this input disappears, is not used. Okay? So that's quite interesting. And what is immediately visible on this circuit is that you see, if you come back to the beginning, the circuit is smaller because there is only 1 copy of F and 1 copy of G instead of 2. And it's actually exponentially smaller in the case where you have FGH and so on. So it's an immediate observation that if you allow cycles in circuits, you can be exponentially smaller in size with exactly the same efficiency in time. Because anyway, you have to compute FG or GF. And here you compute G first and F then, And so there is no penalty in time and a huge gain in space. So that's very interesting. Good. Another reason is symmetry. And I think this reason is even more compelling. So here is a very interesting protocol. It's a simple token-based scheduler where you have people asking for a resource by request here, and they may get a grant. Only one of them may get a grant at each time. And here you see you have a token that decides who will be the first one. So here, when the token is here, this is the first one. If it sets rock, then it gets OK. And all the other one, because they will get this wire to 0, all the other one are not allowed to take the resource. And the point here is that this token will change at every cycle. At every cycle, the token moves by one, and this makes the arbitration fair. At first cycle, Mr. Purple is the first one. Mr. Green is the first one at second cycle, and so on. So only one person is served at each cycle. If there is one client, it will be served anyway. And it's fair. It's a fair arbiter. It's very nice. But it is cyclic. It is cyclic. Here I put it with 2 only, simpler. It is cyclic. There is a static cycle in the network. And so normally it's rejected by systems. But it's perfectly sound. Why is it sound? Because you have a token here, a 1. This is a 1. It's just like putting the ears on the Mickey Mouse register. Because if you put a 1 here, this used to be an OR gate, but this OR gate disappears and the cycle is cut here. There is no more cycle here. The cycle has been cut in this place. And at next there are 2 notions. At next time cycle, at next tick, clock tick, the cycle will be cut in a different place. So in the first example, it was 1 input that decide where the cycle is cut here or there. And here it is 1 state of the memory which will decide the same. Okay? So the cycle is a fake cycle. It disappears. And you can make a cyclic design with exactly the same function, but it becomes really ugly because you have to cut the symmetry. There is no reason to cut the symmetry anywhere. This is a little more delicate because if you have no token in registers, then the cycle becomes bad. Then the circuit is nonsense. You need at least 1 register. If you put 2 registers, there is no cycle, but there is no functionality either. So in fact, it's useful with 1. And if you put 0 registers, then it's bad. That means that you have to be careful. Sometimes the circuit is good, sometimes it is bad. And the game is to discover what it means to be good, what it means to be bad, and when is the circuit good. Can we decide that? Can we have algorithms for that? This is a more interesting circuit, which is a real one. I worked on that a lot. It's called the instruction length decoder of the Pentium. And that's a critical circuit in the Pentium. That's the one that takes the flow of bytes from the instruction code and cuts at the instruction boundaries. And there are about 1,000 instructions in a Pentium. And the machine code is very complicated. So the thing is like that. It's a 16-bit circular buffer in which you have buffer coming in from different memories in random orders that come from caches. You can never know when a byte will come in. They don't come together and so on. The length of an instruction, the thing you want to compute, depends on the first byte always, and maybe a variable number of other bytes. And maybe it's complicated. Maybe you get the first byte that says you have to look at the third byte, and the third byte that says, no, you have to look at the 5th byte, and so on, and the length can be arbitrary. So it's a complicated thing. And it's a very nice cyclic design. It's hard to make acyclic. So let's see how it works. There is an initial thing here, that a mark here, that says this will be the place where the first instruction starts. Okay, now you will receive bytes. So I tag it 1. You will receive bytes in any order here. And here, I receive a byte at 1, so maybe I know where 1 finishes. And indeed, it is the case. So I don't have the text of the first instruction, but I already know that the second instruction will start here. Good, so I put my mark 2, and I keep receiving bytes. Okay, maybe I receive a byte as 2 now, and maybe that's enough to know that the third instruction starts here. but I don't even know the first one yet. I don't have the full text of the first one. And then I will receive other bytes here, okay, here, here, and maybe now I know that the fourth instruction starts here. But I still don't know what the first instruction is. So you have to be careful because this byte here, when it will come in, is not a byte of the fourth instruction, but a byte of the first instruction. Okay. Then I keep receiving other bytes, and then, I receive this. But this is the byte of the first instruction, so now the first instruction is complete, and I can feed it to the instruction decoder. And I keep receiving other bits, and maybe at some time I receive the bit, which is now the bit of the fourth instruction, and then maybe this will determine the length of the fifth, and right away the length of the fourth, sorry, and right away the length of the fifth. So maybe I determine two instructions in a row. And that's very important because this design has to be faster than the Pentium actually. And so this design is very nice, and it's sort of very hard to do, I can tell you. It's a design, it's one of the designs at Intel which is entirely checked by formal methods, by formal proofs, actually model checking, because they change it very often because it's critical for performance, and its specification is quite clear. And so it's not tested anymore, it's proven all the time, but by model checking, because it's a good candidate for model checking. But it's a smart design. I mean, you can take a lot of time to get it right, and to get it efficient, it's another pile of time. Good. Again, this thing is completely cyclic. There is no reason. In the beginning, one part is specific, but after a while, it's completely symmetric. And so it's hard to make acyclic. So that tells us that cycles are interesting. Now we have to understand what they are, because not all cycles are good. So there are three kinds of cycles. The first one are the good ones. We have seen good ones. Good. We want these ones. And we want to compute whether how long the time they take to stabilize, how different they are from acyclic designs, and so on. Good. You have the bad ones. The bad ones are, well, nonsense Boolean equations, like x equals x. X equals x, you can see it as a non-deterministic Boolean equations, but in circuits, you need just a wire connected to itself. What is the voltage in a wire connected to itself? Doesn't make sense. I mean, it does make sense, but it cannot generate any value. X equals not x is more interesting. If you put that in electronics, it will make a nice oscillator. Probably not nice, by the way. It makes an oscillator of some kind, depending on the technology. But it's certainly not a digital object. It doesn't compute 0 or 1. It's an object we want to reject for this purpose. It can be used for other purposes, but not for digital circuits. And there are the weird ones. The weird ones are the ones that have a unique solution, but an unclear electrical stabilization. So the most interesting one is x equals x or not x. Took us a while to realizing that this is the most interesting one, but the key is there, x equals s or not x. And of course, for a classical logician, it's true, but for an electronics guy, it's not true. It depends on the delay. For example, if you put a delay, I didn't tell yet, but it's a delay, but you can imagine that is when you change the input, you have some delay before the output changes. If you put a delay, you put a negation here. This is OR gate, x equals y not x, okay? If you put a short delay, a long delay here and a short delay here, what will happen is that, assume you have a 0 here, this 0 will enter this delay, here will be changed into 1, assume this is no time, will be changed into 1, then after a short delay, this 1 will be coming here, change into 0, this will oscillate, and this guy here, which has a delay of 5, what does it mean? It means that it needs its input to be stable for 5 units of times before going to its output. If the input is unstable, it doesn't drive its output. So this guy will always stay stuck to 0. So if you start with 0, this is oscillating to 1, and the 1 is too short to get out of this. If the 1 gets out of this, then it's all stabilized, of course. Okay, so if you put 5 and 2 instead of 2 and 5, then it will stabilize to 1. So this circuit stabilizes or not depending on delays. But depending on delays is not something we want to deal with because we don't exactly know the delay before the very last day of the implementation, and if we port the design to another technology, it will be different. So we are interested in things that stabilize for all delays. Okay? So this guy does not stabilize. So in fact, we called it Hamlet because it's solving the equations to be equals to be or not to be. That's exactly what the Hamlet play is talking about, by the way. And the key observation is that it does compute 1 in classical logic, but not in constructive logic, because it uses excluded middle. And that's interesting. So the question we ask, can we characterize the good circuits, the one that electrically stabilize in a stupid way, all the one I have shown before were stabilizing in a stupid way, exactly as stupid as for acyclic circuit, just by propagating input values toward the outputs, and not by internal strange effect of delays and so on. So the idea is here that the idea is very clear, is that electrons never heard of the excluded middle law. As we say in French, les électrons ne sont pas au courant de l'existence de excluded middle. So, what we want to do is to formally study the relation between a reasonable electrical model and a purely logical model. And we already know this is not classical Boolean logic. We want to model stabilization only because of inputs. Inside the circuits, before stabilization, anything can happen. You can have transients, you can have all sorts of the glitches or whatever. We want to ignore that. We are interested only in the stable part. And we want to go from theory, real theory, I mean, to practical algorithm, that here we want to be able to build these circuits and for them to work. And we want also to be able to formally verify them. And because synopsis or cadence, the CAT systems want us to be acyclic, we want to automatically produce acyclic versions and maybe be able to prove the equivalence automatically, the equivalence between handmade acyclic versions and the original cyclic version. We want all of that. Otherwise, you don't play in this game. So let me call constructive circuit a circuit where the outputs are electrically stable for all wire and gate delays only by voltage propagation from inputs. Okay? No strange memory effect. There are delay models that have lots of defects from them. So the theorem I will show, no, I will not show, I will explain. The proof is not too easy. Is that three things are equivalent. One, the outputs are computable to 0 or 1 in constructive deducted logic, so that's the logic view. Two, I forgot something here. Circuit is constructive if I just forgot the statement. Oops. Sorry. Okay. A circuit is constructive if its outputs are computable to 0 or 1 in constructive deductive logic, or to 0 or 1 in the Scott logic or in Kleene logic, bottom 0, 1, which is the same. And that gives algorithm to test electrical constructivity. So you see you have one world, which is the world of electricity, where you have real delay with real numbers as delays, electrical propagation, so that's a very complicated transients, all sorts of things. That's a very complicated world. And you have a very simple world, which is constructive logic, and they are equivalent. If and only if. Huh? What is constructive Boolean circuit? Logic. Well, your circuit is a set of equations. You have a set of equations, x equals some expression. And we start from inputs. So I is a function from inputs to 0, 1. You set the input to given values. And the formula we want to deal with in the logic is given these inputs, this circuit, this E will evaluate, this expression E will evaluate to B. And since I will be constant all over the execution, I will not put it in the, I will factorize this out, okay? So here are the rules that are horribly simple, the most stupid constructive rules you can think of. For an input, you just take its value. If you can prove that E is 0, then you can prove that not E is 1. If you can prove that E is 1, you can prove that not E is 0. For an end, if you can prove that one of them is 0, then you can prove that the end is 0. And this is a parallel end. Theorem by myself and previously by Plotkin. This function does not exist in C. Interesting, in ML, in lambda calculus. It's not definable. In circuit, that's the only thing we have. And here, if the two values are 1, then the intersection is 1. Okay, that's the most stupid definition. Or is dual, and that's the most important rule, of course. If you have an equation like that in the circuit, X becomes E. That's a definition in the circuit. And E, you can prove that E has value B. Then you can say that X has value B, which means that you orient the rules from right to left. Okay, it's hard to find a simpler definition. And this simple logic will characterize exactly the right electrical real-time behavior.
What's the difference between double dot equal and...
Okay, equal is equality.
Yeah.
And double dot is circuit definition. The wire X get the expression E. I didn't want to use, this is a circuit equation.
So your theory, eventually.
Huh? Eventually. It's what you would, yeah. Electrically, this means eventually X will be the value of E. Okay, and this is Boolean equality. This is why I use two different symbols. This is the thing you write in your circuit definition. X equals E. Usually you write equal, but so far we are not sure equals means equal, and the theorem will tell yes. Okay, if the circuit is good. Okay, this logic is obviously intuitionistic. That is, there is no excluded middle. You can prove, of course, that E or not E is 1 or E or not E is 1 if E is 1 or E is 0. But if you don't know anything about E, you cannot know anything about E or not E. Fair enough. So that's not a good rule. These good, the others are good, it's not a good. And of course, to prove E or E prime, you have to prove E or to prove E prime, which is the essence of intuitionistic logic. Good. So that's very different from Boolean logic, because Boolean logic, X or not X, is true, and so Hamlet, to be or not to be is true, and the play is finished. Okay. So the fact is electricity propagation is intuitionistic, and how do we prove that? How do we state that, by the way? Now we have to deal with delays. We have to explain what delays are. So there is a big debate about what delays are, but because I stated that what I want is a stupid model where propagation depends only on propagation of real values that are computed for real reason, this is the logic that has to be used. Basically, what we do is we shall put delays in the circuit wherever we want. A delay assignment, you put delays wherever you want. You have to define what is the delay. The only constraint is that there should be one delay per loop. If you have no delay per loop, you cannot do a theory of circuit electricity, by the way. Okay. And for the rest, I say that all the logic gates are 0 delays. I can do that because since you can put delays everywhere, if you want to have the logic gate that have delays, then you can just put a delay at the exit point of logic gate. So you can place your delay arbitrarily. And the theorem will tell you it doesn't matter anyway. So you place your delay wherever you want. And then we are allowed to group, to do conventional Boolean algebra on the other gates, that is to group them. Why? Because we shall use these gates only with defined values. So only when the Boolean algebra is indeed valid and equivalent to the constructive one. But that simplifies simply notation. So for example, this here will be S1, Y1, where is Y1? 1 here is X bar. So this is a notation for not. Y1 is X bar. S2 here is S1X. So here I use the polynomial notation because I have many Boolean calculi. So for the basic case, I will use the polynomial notation. So product is AND and sum is OR, and this is negation. So I say here S2, where is S2? S2 is the output of that, so this is this. It is the sum of S2 and the negation of the n of S1 and x, so that S1 x bar plus S2, which is the same as S1 bar plus x bar plus S2, because here I can use the Boolean calculus because I will only use these things when the values are okay to use these things. And I have explicit delay nodes with delays value, which are real numbers, and what needs delay per cycle. Good. So that's a delay assignment in a given circuit. You can have as many delay assignments as you want. What is an history? So our history will be relatively abstract objects because essentially we assume that we have two values 0, 1, which is not true in electricity, but doesn't change anything. We have 0 and 1, and we switch in no time from 0 to 1, which is not true in electricity. But it doesn't change if it takes some delay. You just add the delay gate and you get the same thing. So basically, an history is the right continuous function from the real positive numbers to 0, 1. Why right continuous? Because you have a little problem where you have an instantaneous switch. It is in fact stupid to draw this line, but it's convenient because it's traditional to do it. And so right continuous means the value is not the one before, it's the one after. That is the value when there is a change, is the new value, not the old value. That's just saying that. Good. So we shall work with semi-open intervals because of this high continuity, written this way, bracket TU, T is included, U is excluded. In the paper we use this notation which is somehow easier to read than this one, which is more useful, but more classical, but that's the one we use. Anyway, there will be no difficulty with that. And so when we take a history and an interval, we can slice the history through the interval, and we can take the part of the history contained in TU, and of course excluding, in case U is itself an edge, excluding this value. So this is this piece of history up to U not included. Good. What is the thing we are dealing with is satisfaction of a predicate P by a history slice. This will be our basic formula we deal with. This is the logic will be about that. The model will be about that. This is where there are two bars here. We are dealing with a model, not with a deductive calculus, which will come later. Good. So, what is the delay? A delay, we have a lax definition of delay. That is, a delay is a very simple constraint. It says that if the input to a delay here, the blue input, is kept constant to some value for the duration of the delay, then the output will take this value. So the delay is simply a thing that says if you keep your input long enough, then your output will take the value. No other constraints. You see, if you don't keep it enough, anything can happen on the output. There is no coupling whatsoever between the output and input. So this is a model which is very permissive, which is what we want, because we want some other models may have electrical connection more complicated between input and outputs, which means that they may have stabilization only because of particularity of the delay system. This is the most general delay system. So remember, stabilization of input is stabilization of the output. Yeah?
Stupid question. What does UN stands for?
UN is up-bounded non-inertial.
Thank you.
I can explain that later. I can explain that later. Up-bounded non-inertial. So we say that the history, we are interested in stabilization. That is in values staying to their value 0 or 1, okay? We say that the history is stable at some Boolean after a delay if from this delay to infinity it has the value of this Boolean. In practice, we do not care about infinity because when we have stable value, we give other inputs, but we study only one infinite cycle here. Otherwise, a history is called unstable or oscillating. That's the same. The hardware vocabulary is not that precise. Okay, so definition, a circuit with delays is constructive with respect to a set of stable inputs and a set of delays if all its inputs stabilize to the same value for all execution histories. That is, whatever you given in input, you get a deterministic output, which is, by the way, exactly the one of the equations. You can say it is uniformly constructive with respect to a set of inputs if that is true for all possible delays. And you can say it is uniformly constructive if that is true for all stable inputs and all delays. So circuits without cycles are uniformly constructive. There is no problem in there. And the question is, what about cycles? Here is the predicate logic. So that's the important part of the model. So the formula are very simple. So this is a Boolean predicate, we call it origin, negation, intersection, union, implication, equivalence, and delay. It's a model logic of a real time with classical operators, not classical, with standard operators and delay. So what is a region is simply a Boolean predicate. Simply a Boolean predicate. So a region is true if the Boolean predicate is true. For example, x, y, so x is true and y is true, or y is false and z is true. So that's simply a Boolean predicate. It's called a region. Or it can be empty, which is false always. And we use, again, to avoid confusing the different logics, for the basic Boolean logic, we use polynomial notation. And for the circuit logic, we use the and/or notation. Good. So what is to satisfy a region, it's very simple, is that during the whole interval TU, the history satisfies the predicate. That's fine. For example, x is stable to 1. Okay? X is stable to 1 from time t to u. This is simply written. H of tu satisfies x. Same for x bar. So this is a logic that expresses stabilization in a very simple form. Good. And of course you have formulae, that is, this formula says x is stable to 1 and y is stable to 0 within time in a history or history set h from t to u. Good. Conjunction and disjunction are simple. You said simply that a history satisfies a conjunction if it satisfies both. A history satisfies a disjunction if it satisfies one or the other. This is clearly an intuitionistic disjunction, okay, from the beginning, because here we deal over time. Huh? And what is to satisfy a delay, which is the most important statement, of course, you satisfy a delay d phi, a property phi, if after, in the interval tu, after waiting d, the property is satisfied. That is, if it satisfies from t plus d to u. That's where the delay occurs. Yes?
Another stupid question. What is the type of D, red D?
Delays here, the type is real, a real number. And I put it in purple because all the delays will be purple just to recognize them. That's all. It's a real number. T, U, D are real numbers.
You mean positive real numbers?
Positive real numbers.
Okay.
Positive real numbers. Sorry, R plus. Okay? So here is, for example, a history of one signal, and you take a slice, and for example, here x is not satisfied because it oscillates between 0 and 1. So x is not always satisfied, but x is delay d. X is satisfied because after a delay of d, x is constant to 1. Okay? So that's a very simple logic. Good. And that's the same if you have okay. Negation. Here is an interesting thing. X stable to 1 is HTU satisfies X. Logical opposite is HTU doesn't satisfy X. But this is not what we want. Because any unstable signal doesn't satisfy x. What we want is the negation of x to be the negation of the value. That is, a stable value 0 will be negated into a stable value 1. So we want not x the same as x bar over time, which is different. For example, here, this guy satisfies neither x nor x bar, okay? And so what we have to say is the following. That's the most important definition of all. We say that HTU satisfies not phi if it doesn't satisfy phi for any subset of TU, any subinterval of TU. Okay? It is never allowed to satisfy phi. So here, for example, this guy doesn't satisfy. You choose your interval, okay, chunk chunk. So this is the most important thing, this quantification. It should satisfy never. It should not. It's not allowed simply not to satisfy. It should never satisfy x. Okay? And this never is represented by subintervals. Phi is never satisfied by H and TU. Good. So then implication and equivalence follow because you know that not x is x implies v empty. And so the same you have to put here this satisfaction here. And so that becomes very interesting. Here is the full logic, so it has nothing complicated. So N and O are trivial. Look trivial, sorry. Not is quantifying, and amplification is quantifying, equivalence is quantifying, and the delay is simply the delay. Good. So of course, as usual in logic, we say phi satisfies psi. You see, whenever an history satisfies psi, then it satisfies phi. I try to keep the meta logic in blue, because there are now 3 levels of logic, the gates, the logic of real time, and the logic of reasoning. So phi satisfies psi. It means that whenever you satisfy phi, you will also satisfy psi, no problem. Good. What are properties? First, it does express stability. What is to say that a signal is stable is saying x or not x. X or not x is true as soon as the signal is stable. So that's very nice. Then I write that x converges. Excluded middle doesn't hold because x or not x doesn't hold whenever h is unstable. So excluded middle really, x or not x is really the key for stability. This is why intuitionistic logic is very important here. And disjunction is intuitionistic. It chooses this camp. Okay. If you have in some interval you satisfy phi or psi, you cannot satisfy phi at some point and psi at other point. You can satisfy either entirely phi or entirely psi. Good. How do we encode circuits with that? Well, that's fairly easy. When we want to say that an input is 0 or 1, we say that we say delay 0 x for 1 and delay 0 x bar for 0. We could say x or x bar, but that will be simpler. It's equivalent. So, that means x is always true and x bar is always true for 1 and for 0 respectively. Gates are directly encoded by Boolean expressions, and delays are encoded by delays assignment. Delay assignment is written like that. Y becomes x after delay d, which is what you wanted, Jean, meaning the following. If x converges, then after delay d, y converges, and if x is stable, if you want, after delay d, y becomes stable and equal to x, which you can also write in a more interesting form. If x becomes stable, then y becomes stable to, if x is stable to 1, then y becomes stable to 1 after delay d. And if x becomes stable 0, then y becomes stable 0 after delay d. This is equivalent, but this form will be more interesting in practice. That's the definition of a delay. So example here, if I put my Hamlet with delays, I will have this formula. Z is Hamlet plus an extra gate, just for decoration, xy, and y is S1 plus S2, and S1 becomes y bar after, because of the negation after delay d, and S2 becomes y after the delay d. Now what we can notice right away is that the only thing that matters is stabilizing the delays. Because since the other gates are assumed 0 delay, if you stabilize the delay, everything is stable right away. So we can simplify all the equation, just take care of delays and the equation of delay relative to delays, and say that what matters in the circuit is that S1 after delay D becomes S1 bar and S2 bar, which is S1 or S2 bar, okay? And S2 becomes S1 plus S2, it's just written here. And the other variable will follow if you stabilize delays. Good. So here is the formula to describe this circuit here without inputs. And if you want to add inputs, you just add input is 0. So we can encode in the logic, we can encode the circuits very nicely, no problem. Okay. And we obtain some formula, which is a big end, okay, of subformula. We can obtain this formula, which I call the formula of the circuit for input I. And this formula encodes all the electrical properties of the circuit. Okay, theorem 1, modulo Zeno, of course you have Zeno on the way. Zeno history, but you can get rid of them as usual. It's boring. Circuits are adequately represented, that is, history is correct for a circuit and inputs I if and only if this predicate is verified. Okay? Corollary, that's interesting. A circuit is constructive for a set of delays and an input I if there exists a unique value S of its delay variables and a global delay D such that phi of Ci stabilizes to S into value D. So the constructivity is, it says the same, it says constructivity is represented, and there is a fixed delay because there is a fixed number of delays in the circuit, in fact, and that's enough. So the logic does represent stabilization of the circuits, but that's fine, but what can we do with it? We have a logic, we have formalized, people like formalizing. My experience is that if you buy enough Greek letters, you can formalize what you want. But in programming, yesterday, Xavier Leroy said that programming languages have been formalized in book of Greek letters that have no use whatsoever. So that's not what we want. So now we want to be able to understand this logic. And to understand the logic, the only solution we have is to make a calculus out of this logic. So, calculus. What is the calculus? We want to compute what's happened in a circuit. In fact, we want to simulate the circuit. And then we shall use exactly the Curry-Howard principle. Computation is deduction and conversely. So we shall do our simulator based on deduction, on a deduction scheme. So here is the deduction scheme. So first we say we deal with timed regions. Time regions is the thing that we want to deal with, stabilization basically. That says that a time region is a predicate that becomes true after some delay. And our right-hand terms in the deduction will be a big union of things. Typically, all my outputs get stabilized. This kind of formula you want to write. Okay? So the sequence will have this form. Given this circuit and these inputs, this time region is true. That is, these properties of the output, typically, or wires, will be true. This is what we want to compute. And this is a very particular structure because these are horn clauses, basically. You have a big end on the left, you have a big OR on the right, and you want to compute that. And so there is a lot of theory about and practice about computing these kind of clauses, of course, which means that it will be easy to automate. You just write the thing in Prolog, and you hit in a relatively smart Prolog, you hit return, and you get a circuit simulator. Real-time circuit simulator. Good. But now we have some other thing. We have the model. So we have this logic. I didn't show you the logic yet. We have this logic, and we have the model. And what we want to have, of course, is equality of the logic in a deduction for this kind of formula. This logic is able to write many more formula than that, but we are interested in simulating circuits. So for this kind of formula, we are interested in knowing whether these two things coincide, and I guess you have understood that the answer will be yes. So what is the what is the deduction? A deduction is very simple. It's simply you deduce some timing properties, some time region, if there exists a sequence of timed regions such that either it's given in the circuit, which means it's an input, or it's deducible by a deduction rule. And now we have to see the deduction rules. Oh yeah, that's for one time region. And for a union of time regions, which may be infinite, which will be infinite, by the way, only if it satisfies the union, if and only if it satisfies at least one of them. Intuitionistic satisfaction, no problem either. So what are the rules? The rules are very simple. So again, because this circuit and input will be fixed, I will forget the term style. So the rules, the first rule is indispensable for completeness, but it's not saying much. Says that true is true at any delay. The second rule says that it's a weakening rule that says that if you have proved that a certain region is satisfied, certain predicate is satisfied after a delay d, and if you take a longer delay and a weaker predicate, then the predicate S is satisfied after delay E. Trivial rule, weakening, standard. The chaining rule, which will do the calculation, is also trivial. It says that if you satisfy a property R after delay D, and if R implies in the logic, if R implies that S is satisfied after delay E, then S is satisfied after delay D plus E. This will allow us to traverse gates. But it's trivially logic. In logic, it's completely trivial. And remember why it will be useful, because this is exactly the definition of a delay element. A delay element is exactly this shape. If X is true, then Y becomes true after delay E. You see? This is why you can apply it. And the last rule is join. That's more interesting. This is dealing with parallelism. You regroup parallel computation. And it's very trivial rule. It says that if S is satisfied after delay D and T is satisfied after delay E, then S and T is satisfied after delay max DE. And of course, this is saying that you have to wait for the maximum satisfaction of your input. And that's all. And that's all. And this is enough now to simulate circuits, so let's do it. No, that's not all. You had classical Boolean rules for region, no problem. And you add arithmetic operation for delay, that is 1 plus 2 equals 3. You are allowed to do that. Okay, let's take our circuit and compute it using the rules. Only the logic rules, no more, no intuition, nothing. So I start with x equals 0 with the circuit. Okay, so what can I say? I can say that I can take this predicate, x is 0 always. That's an hypothesis. It's in I, in my inputs. Now, by rule chain, I can deduce, because I have this equation here, I can deduce, this is also in the hypothesis, so I can deduce that after delay D1, S1 becomes true. Now I can take this guy again, and I can, by the weakening Boolean rule, because here I have x bar plus S1 bar plus S2, since x bar is true, this whole thing is true, by weakening normal Boolean reasoning. Okay, I can deduce that. Okay, so I know the value of this expression. So after delay D2, I know the value of S2. And so now I know the value of S1, S2 after max D1, D2. It's just doing exactly what any circuit simulator does, but now it's expressed in deductive calculus, which will allow us to prove the thing. While in simulator, it's not allowed. The only thing a simulator can do is allow you to look at things, not to prove them. So we say that if x is 0, it remains 0, it's stable 0, then region S1, S2 is reached in time max D1, D2. Good, and actually this is the only region that is deterministic. Now if you put 1 instead, you have a delay 0x, so you can take delay 0x. From that, by rule chain, you can and rule bool, which I forgot here, you can say because x is true, x bar is 0, and S1 becomes false at delay D1. Now here, because you take this deduction again, you put it here, And because of that, you have S1 bar here. So by weakening, you can say that this expression becomes true after delay D1. And so we can say that because of that, this expression, the D2, which is the left-hand side, becomes true after D1 plus D2 this time. It was not max, it is D1 plus D2. And so by combining the two, you say that after max of D1 and D1 plus D2, S1 bar plus 2 is true. And this is, of course, this is D1 plus D2 by Boolean computation. So you can deduce that. So you have proved that your circuit is, you have proved that the deduction calculus has told you in both cases that your circuits compute whatever, exactly what you want. Okay, but that doesn't tell you that you're right. And to tell you that you're right, you need theorems. And so here are the main theorems. Well, you can, as you can expect, modulo Zeno again. It is the same to be true in the model and to be provable in the logic. And of course, that cannot be a simple theorem. One direction is obvious. That is that the calculus is fair to the logic. If you look at what the calculus does, there is no problem. And in the other direction, of course, it's not obvious at all. What you have to prove is that if a design is not provable, then it is necessarily oscillating. And you have to prove that by constructing a counter model, as usual, and the proof is involved, and it's not even in our paper, it's in another paper. The proof is seriously involved, but it's completely intuitive because there is no surprise. I mean, it is what you think it is. That is, you have to build, you have to take all the operator and to build by hand the oscillating as we did for. Actually, it gives you also a way to build the oscillation. The other theorem, which is interesting, very interesting, is that this double bar is indeed inductionistic for this kind of sequence, and because the other one is inductionistic by definition. Okay? Good, so that's immediate. Okay, but now the real corollary, and that will end today. Tomorrow we shall make use of that and show you that time doesn't matter. The real corollary, this one, I will end with this proof. Stabilization is deterministic. That is, given a delay assignment for a circuit, you take a circuit, you take a delay assignment, you take an input vector, then the histories of possible in the circuit have only two possible behaviors. One, all the histories stabilize to the same value, the good case. All of them get deterministically to the same value. This is exactly what we want, exactly as in the acyclic case. Or there is at least one oscillating history that you can build basically, constructively. And it implies that the circuit is constructive if and only if outputs cannot oscillate also. So either you get determinism and perfect behavior, timing predictability, either your circuit which has cycle is exactly equivalent, behave exactly the same as a circuit without cycles, or there is an oscillation. There is nothing in the middle. Okay? So let's prove it. Let's prove it. My bars are misplaced. Okay, this bar should be here. So you make a verbal, mental translation here. That's a disadvantage of the notation. So if you have, let's look at this infinite formula, which is the trivial. It says S stabilizes to 1 in time 1, or S stabilizes to 0 in time 1, or S stabilizes to 2 in time 1, or S stabilizes to 0 in time 2, sorry, or 2, or 3, or 3, or 3, or 3. That's a stupid infinite formula, which has no problem with Zeno, by the way. And this stabilizes eventually. So it's a very heavy way to say it stabilizes eventually. Okay, so there are two cases now. Either this formula is true, then it is true for at least one of the predicates, K. So it is true for this predicate. But saying that it is true for this predicate is saying that, for example, S becomes true after time M. And that's a property, by definition of satisfaction, that's a property of all histories. So it is good, it's saying all histories stabilize to the same value. Or, case 2, this property is not true. Then it is impossible that all, by definition, it is impossible that all histories satisfy this formula, which states that there is a history which doesn't prove this formula and which is a history of the circuit. And since it doesn't prove this formula, it must be oscillating. Period. So the key is, of course, in the counterexample construction. But once you have done the comparison and you play with intuitionism as usual, then you prove that there are two cases. If this big formula is provable, then all histories stabilize. And if it's not provable, that there exists an oscillating history. And that's it. Okay. So it is exactly time. So tomorrow we shall show that time doesn't matter. You can remove it. And that will end the thing by saying that but since you can remove time, let's do it. And that means that computing whether a circuit stabilizes for all delay has become a completely constructive Boolean problem. And we shall see that we can translate it into a classical Boolean problem and use BDD and SAT and whatsoever to solve it and have very good algorithms to decide that, to compute times and so on. That's it.
Questions?
Two little questions. Maybe it's I missed some point. So there is usually the semantics for intuitionistic.
Could you put
usually yeah. Usually the semantics for intuitionistic logic is given by what people call complete typing algebras. And it's interesting to find a single one, yeah, where interpretations in this single one give you constructive validity. And it's known from the theorem by Gödel from the 30s that you cannot do this via a finite thing. Yeah? So what it works for is a collection of open. Oops.
Yeah, you should give it horizontal.
The collection of open subsets of pair space. That's a universal model that plays a role for intuitionistic logic, what two-valued Boolean logic does for classical logic. The question is, in your model, can this be considered as a sort of complete typing algebra? Which one? And the second thing, I did not see implication in your calculus. Could it be that it's a fragment of intuitionistic logic where you do not have implication?
Well, there is implication, yes. There is implication. Sorry, you didn't see implication because I use this notation. This is implication. Huh?
Yeah, but it's a basic thing. It's not defined by the rest.
No, it's a very basic logic. Huh? It is a completely basic logic.
Logic.
Yeah, it's a we don't need a complex logic at all.
Yeah.
The idea is that people have been trying to play with complex logic, and that was a very good idea. For example, there are logics where you study all the transients, and you show by complex argument that all the transients disappear after exponential time. It's just completely useless for this problem, that's all. So you may have a much more elaborate logic. There are also phenomena we cannot model in this logic, like metastability and things like that. So for algebra, I mean, the other presentation of this is with three-valued logics, of course. I mean, instead of having constructive, I'll show you next time.
But it's three, and by Gödel we know we cannot work with a finite complete typing algebra. It has to be infinite. I mean, open subsets of pair space does the job.
I don't see why here, because our problem is entirely finite. There is no infinity in our problem at all. Everything is bounded. It's completely bounded. There is no infinity comes from nowhere here.
Yeah, but I mean, But then your calculus cannot be full intuitionistic logic.
No. It is not full intuitionistic logic.
So what's missing then? Implication you have. So which fragment of intuitionistic propositional logic is it then?
Oula, I'm not sure I can answer the question. I mean, the guy to ask the question is Michael Mendler.
Okay.
He's the real guy of the proof. Huh? I'm the teller.
Fair enough.
I'm the storyteller. He's the real guy of the proof.
Okay.
No, in fact, the way it has been done, is that I got the ideas basically. Basically, Hamlet tells you where is the problem. Okay, and then a first proof was done by Tom Scheipel at Berkeley, and Tom was at Digital Equipment at the time, and using another logic called the UI logic, inertial logic, which is a very strange logic because it has all sorts of bad consequences. And the proof was really very involved, and it relies on a book by Brozovsky and Zeger on the behavior of asynchronous circuits. And then Michael Mendler took the thing and say, we have to be stupidly intuitionistic. So it's a stupid intuitionistic logic. It's not expressive. You cannot express very much. It's made to express exactly stabilization period. You cannot discuss anything else with this logic. This is why it's not complete for anything. It's just meant to solve this problem. But the counterexample is as usual. The construction of the counterexample uses a classical technique. It's not a powerful logic at all. You cannot express very much. You can express things about finite Boolean circuits. But it was fun to see that wherever people have been doing hand waving, because real nature is people say, well, this worked because I tell you it worked. Huh? So we thought it was not really sufficient, and I think the solution is cute. But it's not, and it's also nice. I think it's a very nice way to explain people you see, for example, when I want to explain that intuitionism is natural, which means it exists in nature, it's a nice way to talk about physics, and also to explain Curie-Howard. To explain that a circuit is making proofs, and that a circuit is a proof network somehow in the sense of Girard, not quite, but it's a circuit, an electronic circuit, is simply a folding of proofs into a graph structure, and when you put electricity, what you do is magically build proofs in nanoseconds. That's fun. Electricity is fast. Light speed's proof. Much better than the lambda calculus for that, I think. The lambda calculus proofs are. And here the machine is trivial. And it also says that, for example, we were with Pierre-Louis, we work on that the only, for example, the parallel OR, the OR gate. OR gate says 1 whenever you have a 1 without caring about the other. This is the only thing you cannot define in the lambda calculus. Theorem of myself, you cannot define this guy in the lambda calculus. So it says these are completely different models. And it's very surprising to see the same reasoning, the same style of reasoning, the same style of mathematics, although here it's much less deep than the lambda calculus. Come here. And I think it's very nice to explain people about intuitionism or about, so you can explain, it's very hard to explain the higher order lambda calculus to anybody. But electricity, no. That's what I liked it. And I think this should be in Coq. Of course.
Okay.
How do we get rid of time?
So before you get rid of time, as you promised to do, how do we have to think of time at the moment? I mean, you say it's real numbers, but what kind of real numbers? I mean, does it play any role? Would it be rational numbers? Would it be constructive reals, Coq reals?
No, it doesn't matter, because if you look at what's happening, the delay is a minimal thing. If you are longer than the delay, it doesn't matter. So if you start with real number, you can take a rational which is bigger than this real, and you have no trouble at all. because you are interested in minimal stabilization time, in existence of minimal. If you take it bigger, it's still good. So you are not forced to care with reals. You can do with anything. You can do with rational, for example.
And therefore you can get rid of them.
The problem is that you have to be a little bit careful. No. You can get rid of time for much deeper reasons.
Okay.
Yeah. No. That's not. No, you can get rid of time because time plays no role in the logic. But the point is that if you get to, you cannot get completely. You still have to deal with Zeno somehow. You have to show that Zeno doesn't perturbate anything. That Zeno is not a problem. It's always true in this kind of logic. It's boring, but I don't see how to forget about that. But since we shall remove time, it doesn't matter what it is. Any algebra where you have max and plus will be time.
You just said it before you remove time, which is a drastic thing to do. All you need is max and plus.
Is max and plus. Before, yeah. In fact, my timing model is not R, it's max and plus anything. Yeah. But people want to have it relation with physics. And I still, I discussed with my colleagues, physics colleagues at Collège de France, for example, with Serge Haroche, who is the head of the college, and got the Nobel Prize in quantum mechanics. I tell him, is time continuous or real? He said, well, you know, time doesn't exist, so I don't know the answer. It's probably discrete anyway. No, they want to stick to the idea of timing networks with real numbers, the Kirchhoff electricity, Kirchhoff laws, basically. This is why the standard presentation is real, but in fact it's max plus I use. So if you want to put it in coq, you take max plus, no problem.
Okay, other questions? Okay, maybe I have one. So, where are the two-adic numbers now?
No, they are not in the same. Not the same talk. Not the same talk. Here we are in no. Here we are in the combinational part. The two-adic numbers are talking about the sequential part essentially. Okay. But then when you have that means that you can build very nice two-adic cyclic circuits. Sure, but I have no good examples yet. The examples I gave are not particularly two-adic. Because the example I gave, if you look at them, for example, the instruction length decoder, they are not playing with numbers but with control, which is something, with finite state machines, which is another. And the relation between two-adic, we use two-adic elsewhere. We use two-adic in clocking systems, in signal processing networks, but then there are more finite automata things than two-adic things, in fact. Not all finite automata are linked with numbers. For example, a protocol is not particularly number.
Okay, so thank you, and we'll meet tomorrow.